Well, good morning there. I missed Sunglasses Day yesterday, so I thought I'd bring it in today along with Jersey Day. Now, I don't have any of those, professional or college team jerseys, so my jersey, specialty from 1986. It's a little bit snugger now than it used to be. Oh well. I did have another option. We had another jersey from 1986, but this was one of those short jerseys, and I didn't think he wanted to see me in that. All right, now try to get those images out of your head, or you're gonna have nightmares. All right, so physics Tuesday, 3/31/20. Let's practice some friction problems on an inclined plane. Sounds a lot like yesterday, right? Well, I'm guessing that your first time trying to do some of those problems on the inclined plane, I'm guessing you got stuck a few times, okay? I didn't hear from any of you on it, but I'm guessing there's some getting stuck. So, I want to work another practice one with you. So I made up my own problem today. Blake's truck breaks down just 400 meters from his driveway. He calls Carson, Ethan, Adam, and Ian to come give him a push. The truck has a mass, with Blake sitting in its steering, of 1,725 kilograms. They have to push the truck up a 6-degree slope. The coefficient of rolling friction is 0.02. Now, we talked about sliding friction and we talked about static friction a little bit. Well, vehicles have wheels under them, and that's a good thing, because if we were sliding our vehicles down the road, we would need a lot more energy. So the wheel and axle system dramatically reduces the energy, or the friction. So that's a low coefficient. I actually looked it up. The friction between like car tires and a gravel road was estimated at 0.02. If the four boys together exert a force of 2,200 newtons on the truck, what is the acceleration of the truck, and how long will it take them to push it the 400 meters? Okay? So there's lots of assumptions in here. One is we're going to assume that they can apply this through that whole trip. So even though the truck's going to start moving faster and faster, or I hope my math comes out that way, they're going to keep applying that force. And so then how long will it take to get to that driveway? All right. So as I read through it, I guess I could have been marking some things already. But first of all, let's identify the questions, okay? What is the acceleration? And how long will it take? So there's two things that we're looking for. We're looking for an acceleration, and we're looking for a delta t, okay? Now let's identify what are the things that we know. Well, right down here I see a delta D, 400 meters. We have a mass of the truck. We have an angle. We have a coefficient of friction, mu. We have a force. I'm going to call this the applied force, because we're applying it. Anything else that we could read into it? The velocity is not constant because we're going to accelerate it. What's the initial velocity of the truck? I suppose we could say that. When he's sitting stationary and has the brake on, the initial velocity would be 0. Okay? But I think that's our information. And if we need something else, we'll come back to it. So let's try to draw a picture here. 6-degree slope isn't very much, so I'm going to exaggerate a little bit, otherwise we don't have much to look at. But this is 6 degrees. And by the way, so I made up the numbers here today, and there's not many sig figs in it. We're going to just go through and try to do this as a concept problem of how to do the calculations. We're not going to worry about the sig figs on this one. I'm just going to calculate everything to 3 digits. Okay, 3 sig figs. Just because I wanted to give you a problem, you know, based on a situation that you could hopefully imagine and see and think about. And so let's just do this without worrying about the sig figs. Let's worry about the calculations. So we've got our truck. There's Blake. And let's see. Think about the forces. The weight of the truck is pulling straight down. That's FW. I'd like you to pause the video, take 30 seconds or a minute, and draw yourself the rest of this free body diagram, labeling in all the forces on the truck. Go. Hopefully you did that, and you got a diagram. Now let's compare. I know that the weight of the truck, part of that weight is pushing perpendicular to the incline, and I'm going to call that F perpendicular, and part of that weight is going parallel to the incline, so it's actually pulling us backwards down the hill. I'm going to call that F parallel. I know that the road itself is supporting that perpendicular force. The road is pushing back with a force equal and opposite, and that's my normal force. So the magnitudes of those two are the same. I know that our group of boys are going to push on the truck this way. That's our applied force. Hopefully they're going to apply enough force to overcome this parallel component of the weight and accelerate it, which means that if it's moving that way, friction's acting that way. So the force of friction is this way. Now look at your diagram. Did you go through the same reasoning? I started with my weight, broke it into components. Then I looked at my perpendicular direction. That's easy. The normal force just balances. Then I looked at all my forces in my parallel direction, and I realized that part of the weight is pulling backwards down the hill. The friction is working against us, but we're going to be pushing forward. So if we think through it in that parallel direction, think of what my net force is going to be. My net force is going to be all the force that we apply minus the forces that are working against us, which in this case are the parallel component and the friction. I really wish I could write smaller on the board and keep it legible. These whiteboards are just not made for friction problems. Actually, I gotta try something. I can't seem to figure out how to change the line thickness of the markers, but if I write with my finger, I think I can actually make a smaller line. I was going to do that and I forgot about it. The net force equals the applied force minus the force parallel minus the force of friction. Okay? What else? I, of course, remember that the net force is also equal to mass times acceleration. Okay? Probably should get in a few more measurements here. The mass of the truck was 1,725 kilograms. And we know that the applied force was 2,200 newtons. Okay? Trying to lay out all the things that we know. I'm also going to write that the coefficient of friction is the frictional force over the normal force. So let's try to plan this out. In order to get an acceleration, I need to know my net force and my mass. I know my mass. In order to get my net force, I need my applied force, my parallel component, and my friction. I know the applied force. The parallel component should be able to come from, drawing a blank on the name. We got to resolve the vectors into two components. Yes, components. I have to find my parallel component. The friction I can get from my coefficient of friction, and the normal force is equal to the perpendicular component. So if I find my components, I should be able to work through all this. Now, we had another question, which is about our time, but once we know the acceleration and we know the distance that we're pushing it, we should be able to use our acceleration equations to do that one. All right, I got a plan. I have to start out with my components. So I know that this angle, the angle in between my weight and my perpendicular, is equal to this angle of the slope. I know that my parallel component is this opposite side. So if parallel is opposite that angle, I'm going to use my sine function. So I know that sine of theta equals my parallel component over my weight. Okay. I'm going to go off over here and let's find the weight, which is m times g. So 1,725 kilograms times 9.8 meters per second squared. Get out a calculator. Oh, can't read that with my fancy sunglasses on. 1,725 times 9.8. 16,905. Newtons. I'll just keep those digits for right now, round off later. Okay, so rearranging this, my parallel component is going to be my weight, which is 16,905 newtons, times sine 6. So my parallel component times sine of 6. $1,767. Newtons. Okay, great. Extend this page a little bit. So my perpendicular component, which is also equal to my normal force, is going to be 16,905 newtons, that same weight, times the cosine. Cosine of 6. So let's find that. 16,812. Let's stop and think a bit. Notice that the parallel component isn't very big. The normal component is quite large. Well, 6-degree slope is not much of a slope. So almost all the weight of the truck is acting down. Almost all the weight is acting perpendicular to the surface. Not much of the weight's pulling it sideways. In this case, it's roughly 1/10 of the forces sideways, and most of it's down. Okay, so what next? How about if we go to the frictional part over here? If mu equals the force of friction over the normal force, then we could say that the force of friction is mu times the normal force. So our coefficient of friction was 0.02 times, we figured out the normal force is equal and opposite to the perpendicular, 16,812 newtons. $336 newtons worth of friction. Okay, we're getting there. All right, now we go up to this special equation that I had to create for this problem, because the net force, you have to apply everything that you know about the problem. You can't just, there is no one set formula. But I said that the amount of force that's going to go up that slope is going to be equal to what we're applying minus those forces that are holding back, and that's the parallel component and the friction. So we're starting with 2,200 newtons up the ramp. So 2,200 newtons up the ramp minus the parallel component, which was 1,767 newtons, minus the friction, which is 336 newtons. So what I have left is a net force of 97 newtons. Ethan, Carson, Adam, Ian, you might be regretting your helpfulness at this point, because that's a pretty small force to apply to a car. So let's see what we get. If net force equals mass times acceleration, then the acceleration equals the net force over the mass. So my net force is 97 newtons, and my mass, 1,725 kilograms. I know that a newton is a kilogram times a meter per second squared, so the kilograms cross off and I'm left with meters per second squared. My acceleration is 0.0564 2 meters per second squared. There's our first answer. Small acceleration. Okay, now how long is it going to take us to push that 400 meters? My equations: VF equals VI plus A delta T. Doesn't have any distance in it. Let's not worry about it. Delta D equals VI delta T plus 1/2 A delta T squared. VI is 0. I know my distance and I know my acceleration, so I think this is what we want to use. Let's multiply both sides by 2. 2 delta D equals A delta T squared. Divide by A. 2 delta D over A equals delta T squared. Therefore, delta T equals the square root of 2 delta D over A. Remember, as we're working through these, you can always pause the video and take some time to work that out. Okay, so delta T equals the square root of 2 times 400 meters divided by 0.0562 meters per second squared. The meters cross off. The second squared flips back to the top and then comes out of the radical as seconds. Delta T I'm coming up with the 3 sig figs, 169 seconds, which means 2 minutes and 49 seconds. All right, so you got not quite 3 minutes worth of pushing. Actually, I think I'm pretty happy with the overall results of this problem, because I had to make some guesses and estimates onto forces and everything else. I did look up some numbers. I looked up what would be a reasonable weight for a vehicle and those types of things. And yeah, I think it's going to take you a couple minutes to push the truck a quarter mile. So here we go. There was another problem dealing with forces and friction and accelerations, all on a ramp. What happens if we're told that something is happening at constant velocity on the ramp? Well, then we've got to know that, the forces applied in one direction have to equal the forces in the other direction. In this case, let's see. Well, we could try to figure out, exactly like how much force would it take, would have to apply just to hold it if the brakes weren't working and we just wanted to hold it in place. We could do those types of things, to try to figure out an acceleration of 0. All right, I think there's another problem. So with this in mind, I want you to take another look. If you got stuck on some of the other problems for today, take another look at them. In some cases, it probably is a good idea if you just start over and try to work that problem again for practice. You have a problem set that I passed out, that I gave you yesterday. I want you to work on finishing that I'd like it done for Friday. I'd like it turned into me by Friday. We want to go, well, we also need to wrap up and do a test on this chapter. And I've got to figure out exactly how I want to do that test. But between Thursday and Friday, I might break up the test into 2 parts, or I might give it to you all at once. I got to plan that out. I got to think that through. But I want this chapter tested and done before we go into our spring break week. And I think we're in pretty good shape for doing that. I got a feeling, if anything, these are types of problems that you need to be practicing some more. So, as always, if you have questions, let me know. Have a great day.